Hi everyone, this is Matt Ingram continuing with a set of videos on estimating LISA values, more specifically on estimating the significance of these LISA values. There are different sets of methods for doing this estimation of significance, and we're going to look at those more closely here. By extension, um, if there are different methods for estimating the significance of LISA values, then that naturally leads to different methods for generating LISA cluster maps, or what some folks call Moran scatterplot maps. Now, these maps will look very different depending upon which method of estimation one uses. So we want to become familiar with different methods if for no other reason than to conduct some sensitivity or robustness checks with our own data. The two main categories of approaches are the permutation approach and the numerical approach, and we're going to execute both of these and then take a look at the results. And the empirical example we'll be working with is the one that we've been calling replication 1 in class. It's the study of homicides in the United States, published in Criminology in 2001 by Rob Baller and his co-authors Luke Anslin, Steve Messner, Glenn Dean, and Darnell Hawkins. We'll be implementing the different methods in GeoDa, Python, and R just to be able to work across different platforms, different environments. The permutation approach is implemented in GeoDa and Python, though you could program R to run the permutation analysis. And the numerical method we're going to implement in R, although again you could program Python to run the numerical method. So this is the way we'll set up the work. We've already done the permutation approach in GeoDa in a separate video, so I'd refer you to that video for that approach. We've also run the permutation analysis in Python, so I'd refer you to that second video. And this third video then is the one that illustrates the numerical method in R. So that is the only topic that we'll be covering in this video. In none of the videos do I cover any of the technical details underlying these methods. So for those technical details, I would refer you to this additional reading work by Dan McMillan in 2003. Also the material in a chapter in the book on applied spatial data analysis with R by Roger Bivand and his colleagues. And then regarding the permutation approach, I'd refer you to Luke Anslin's work dating back to the mid-1990s. So let's move into the R environment and start looking at the implementation of the numerical approach. So here we are in R. You might be using RStudio, in which case your setup might be looking a little bit different, but the content of the R script is exactly the same. Here we've got the R script from replication 1. I'm actually working on April 3rd here, 2015, so I'll just update it quickly. And then you see all the helpful comments, or the orienting comments at the beginning of the R script that I've been including in all the replication. Make sure you have all your packages installed and loaded. I've already done that here, so I won't do that again. Make sure you have your working directory set up. This is my working directory, obviously, so change it to match your file path on your machine. I've already done that, so I won't execute that here. And then load your. I'll just go through and execute it here, so we can check our working directory, make sure that all of our files are in there. I'm just hitting Control R here after I highlight any one line of code, or if you want to set up a whole block of code, you could execute that as well. You want to load in your shapefile. So I'm calling this new object nat, N-A-T, created by the shapefile. Again, this is all repetitive and review from replication 1. You could summarize that shapefile, or we could extract the data frame. Let's extract the data frame and then attach that data frame. Again, the other commands should all be familiar to you by now. And then we have some additional commands here that we're not going to use. If you were missing a projection component from your shapefile, here's some commands to create one and then to transform it. If you had created a new variable and then wanted to add that variable and write the revised shapefile as a new shapefile. You could do that here. And then we could check the basic shape of our shapefile with some quick plots. Let's just create our spatial weights and move on with the analysis. So we want the 10 nearest neighbors. So we need this preliminary block of code. Again, I'm just going to hit Control R. And then we want to create the basic 10 nearest neighbors spatial weights file or weights object. And we want to then do some transformations. So here we create the row standardized version of the weights file, and then if we wanted to do some symmetric versions, we would create the symmetric version and convert it into a list object. So now let's move forward. We don't need to calculate the global spatial dependence. Let's calculate the local indicator of spatial autocorrelation. So this is the basic function. Again, this is just reviewing. Here's some other statistics, the local G. But we basically have two basic methods. There's one basic numerical method where you're using no adjustments. You're not making any kinds of adjustments to the p-values. And this is following then the simple normality or normalization assumption. And this is the command for generating this LISA object. We're going to call it LISA2. And we could, if we execute that, then we could plot a histogram of those values, and you see those there. Now, here are several other adjustments that you could make. The Holm adjustment, FDR Bonferroni, and all of these are explained in detail in the related literature for the package for the local Moran command or the SPDEP under the SPDEP package. But recalling some of the technical discussion of this method from Roger Bivand and his colleagues, they're more skeptical of the permutation analysis, and they think that the only reliable results regarding LISA values are those that are generated with the saddle point or exact methods. Indeed, Bivand and his colleagues recommend doing both of these in succession. So in order to execute those, we need to refer to the neighbor object and then the list object. So I'm just going to create some generic objects here, NB for the neighbor object and W for the list object that we've created earlier. And then this is the basic command that we've already executed for the local Moran. I guess I'm just repeating this again. And then in order to run the saddle point estimation, which is here, and the exact estimation, which is here, you need the data frame, and you need to specify a model with no parameters, basically, with just a constant in it. So if we do that, we execute these two lines, Control R, then we can execute the saddle point. We can estimate the LISA values using the saddle point method, and we can do the same using the exact method. Each of these takes about a minute to execute on my Windows 7 machine. So I'm not going to do those right now. I've already done them prior to starting this video. The means of each of these should equal the global Moran. So if we went back up to global Moran, we could just set list W equal to our weights object, and this is our Moran test. So the global aggregate level of spatial autocorrelation in the data is 0.358. You see this over here in the console. So if we take the average of all of our local indicators, I'm just scrolling down through the script now. Here are the means. The first line is the mean for the basic unadjusted LISA values. The second one is for the saddle point estimation, and the third one is for the exact estimation. I think in between there I just added the global test as well. So let's just hit Control R here. And you see up above here in the console, there's the average of the unadjusted local indicator, 0.358. Then here again is our global measure, it's 0.358. And then it's the same for the saddle point and the exact. So at least on average they're showing no difference. Let's see if individually they show any differences. We could look at the histogram of any one of them. So over here you see already the histogram for the unadjusted version. This is the histogram for the saddle point. Well, let's just use the same bin size here. This is the unadjusted, the saddle point, and the exact. And you can see on the right that as I executed each one, there were some very small changes. We could put them all in a single, combine them into a single graph, and you see that graph here on the right. And you see some small differences. So if you were really if these differences, even small differences, were relevant to the particular question you were asking, you might want to take a closer look at this. Here's a different version of the same graph, just adding some color and making it a little bit more presentable. But what we would like to do is generate these LISA cluster maps. So that's what we do with the code under this set here. We could do these individually with the unadjusted LISA2 object, or we could do it with the saddle point estimation, or we could do it with the exact values. But let's combine all three LISA cluster maps into one graph, and that's essentially what we do with this block of code under here. So we're going to generate our listW object equal to our spatial weights object, generate a new object called a dependent variable, or DV, equal to homicide rates in 1960, which is the DV we're using right now. And then we're just going to execute all of our basic LISA commands our commands for generating the cluster maps, but for each one of our LISA estimations in turn. So let's execute this top block of code before the graph function. Control R. And now in this graphing function, you could include the entire thing if you were exporting a graph here, Portable Networks graphic file out to your working directory. But let's do this without actually exporting the graph, and so we'll just grab the plotting code in between the exporting commands and generate that map. So here we see on the right the three different LISA cluster maps are being generated. On the top is the one with the unadjusted LISA values following the normality or the normalization assumption. Then in the middle is the saddle point version, and in the bottom is the exact version. Again, these are the ones that Bivan and his colleagues would say are more reliable, and in part they say that because they would say these are more conservative in their estimates of statistical significance. So we can see that a little bit more clearly if we display these LISA cluster maps side by side with the ones generated with a permutation analysis. So this is the map that we generated in GeoDa for the same variable, homicide rates in 1960. And you can see that there are larger regions or areas of the country, larger sets of counties, more clusters in the permutation analysis, in the LISA cluster map generated with the permutation method than there are in the LISA cluster maps generated on the right with the numerical method. That's in part why Bivan would say the numerical methods are more conservative. We could also add to the screen here the map generated in Python. So this is a portable networks graphic file exported from Python with the same LISA cluster map. You can see that this one on the bottom left is more comparable to the one on the top left. That's because they're both generated with the permutation method. And they both appear to show larger areas of the country or more units that are cores, statistically significant cores of clusters, or cores of statistically significant clusters rather. There's less white area, less non-significant area in both of the maps on the left generated with a permutation analysis than the maps on the right generated with a numerical method. Another way to think about this is to generate a significance map from, say, in GeoDa. So if we went to GeoDa and using the same space command that we used to generate the LISA map, homicide rates 1960, and let's skip the cluster map because we already have it here and just generate the significance map. And then let's increase the permutations to the same number, to 1,000. So here's the corresponding significance map for the cluster map that we show up above. And you can see here that while all of the regions shown in the map on the top left are statistically significant at the 0.05 level, it's only the ones that are significant at the much stricter threshold, say 0.001 or even 0.0001, really the dark green units in the map on the lower left, that correspond fairly closely with the units identified in the map on the right. So this is another way of visualizing the conservativeness or the more cautious nature of the numerical method that we just executed in R. These maps on the right in R are the ones that are identifying the same units that a very strict threshold of statistical significance would also identify in the permutation analysis. Again, we could check that further by simply going to the cluster map in GeoDa and adjusting the significance filter to 0.001. Excuse me here. 01. So this is at a significance of 0.001. It looks a bit more like the numerical method, or a significance filter of 0.01, a little bit more. So again, just different ways of thinking about how the numerical method is perhaps a bit more conservative than the permutation method generally executed in GeoDa and Python. Thank you.